Okay, so yesterday we started talking about virtual memory and paging. We said that we will take this idea of base and limit registers one step further, and we are going to let each process think that they have own address space, and that address space will be broken into chunks called pages, and the program will not know anything actually. All the paging will be done by the operating system transparently, without any knowledge from the program itself. And the advantage of this strategy will be we will eliminate any need for compaction, because our programs doesn't have to be contiguously stored on our memory, because our virtual memory will be contiguous, like I showed you last time, like this way. Okay, my program will think that it owns the 64 kilobytes of memory, and in this 64 kilobytes of memory I have, I guess, 16 pages. Okay, each page is 4 kilobytes large. But when I store these pages in my physical memory, in my real memory, I will store it in this way. Okay, this page table is called virtual page table, will hold pointers for each page, saying where I keep these pages in my memory. So these are called pages. Okay, each one is a page, and in my physical memory, each of these boxes are called page frames. Okay, when it is physical, it is called page frame. When it is virtual, it is called just a virtual page. Okay, and the word of physical addresses and the word of virtual addresses are completely different, and my program or the programmer doesn't know anything about them. This paging is completely done transparently by the operating system with the help of the hardware, of course, because each memory reference, okay, whenever it occurs, has to be translated from a virtual address to a physical address, and that's going to be done by the memory management unit. You might say that, okay, this would be too expensive, because I mean, if I have to translate each memory reference from virtual address to physical address, that's going to take time. But these memory management units are specialized hardware. They know what they are doing. They can do it very efficiently, as long as my page table is not very large. As you see, this is a page table of size 16, which is not that large, but as we are going to see, why do I keep getting this? I don't have. Where is my zoom? Okay. Oh, okay, here it is. So each page will be automatically translated to these physical memory addresses, no problem, and this is going to be done by the hardware. As I said, as long as this page table is not large, no problem. But as we will see, this table will get larger. Let me give you an example. This page size of 4 kilobytes, like 2 to the power 12, is common. Okay, even today's computers, page size of 4 kilobytes is common. But nowadays our addresses are what is my virtual address? Okay, what is my virtual address size? It is usually 2 to the 48. Okay, so 2 to the 48 is my virtual address size. Okay, virtual address space size. It is very, very large. What is 2 to the 48? It is 10 is kilobyte, 20 is megabyte, gigabyte, and terabyte, right? Is that correct? Kilobyte, megabyte, gigabyte. Did I miss anything? Terabyte, and then what after that terabyte? What do I have? What? Okay, 50, whatever it is. So it is 2 to the 48 is 256 terabyte, right? That's my address space. Each process on today's 64-bit computers can address up to 256 terabytes of data, okay? So the page table is going to be, okay, if this is my memory size, if I divide this to my page table size, I am going to get 2 to the 36. Okay, so this will be my page table size, right? I need to keep this many entries in my page table, and we are talking about something close to, okay, hundreds of gigabytes, right? Is that correct? Yeah, hundreds of gigabytes of page table size. That's not going to be easy to fit in my memory management unit. Okay, I mean, my memory is not that large. I mean, inside my memory management unit, I don't have that kind of a space. So we will talk about this. We will have to handle this. So let's go back to this. Let's look at this simple case where my page table is just very simple. I keep these 16 numbers in my page table, and every time there is a memory reference, I look at this page table and I do my memory reference that way. Okay, so let's look at this example again. Remember yesterday I kind of looked at this, but let's repeat kind of this picture. So again, the same thing. This is the virtual address that comes from the program. This is my memory management unit. Okay, the responsibility of memory management unit is to take virtual addresses. Okay, it will take the virtual address and it will output the physical address. Okay, so I got this. This is my 16-bit, okay, 16-bit virtual address. So my virtual address space is 2 to the 16. Okay, so this one says that I need to find which page, which virtual page contains this address. So how do I find it? I just take the last 4 digits of it. Okay, the most significant 4 digits of the virtual address. Why? Because this 12 bits, they belong to the address inside the page. Okay, inside the page. I have total of 16 bits. Okay, total of 16 bits. If I divide this address by 2 to the 12, that means that I am shifting by 12 bits. So I am getting rid of all of these bits, and I will end up with these 4 bits only. Okay, so this 4 bit will tell me what page I am in my virtual address. So it says that 0010. So it corresponds. This is 000, 001. Okay, this is an 0010. Okay, so binary term. So I look this up. It says that your physical page number is this 110. Okay, so I looked it up. My physical page address is 110. That will correspond to 6, right? So in my physical memory, my page number is going to be this. So I take this number and I take the least significant 12 bits of my original virtual address, and I put this number at the beginning of my new physical address here, and the rest of them is the same, and output this as my physical address. So basically what MMU does is just a simple table lookup. Simple table lookup. I need to keep all these numbers, 16 numbers, in my memory, and for each one, I know where they are. These are the numbers of the virtual pages, and I just make this physical lookup and the table lookup, and will output that one. Okay. So how about the next column? I mean, this ones and zeros. It says it's a present bit. Can anybody explain me why do I have to keep that number? Yes.
Because it says that if it is in the RAM or the hard drive.
Well, it says that, well, exactly. I mean, it says that page number 10. If you need page number 10 from me, okay, I need to tell you where that page number 10 is in the physical memory, but it looks like I don't have it in the physical memory. It is in the disk. Okay, I don't have it loaded because as you know, my virtual address space is much larger than my physical address space. Okay, so some of them has to be out of my memory. Some of them has to be on my disk. Okay, so these are the absent present bit. So my page table has to keep that information too. So far, my page table for each entry has to keep two things. One is the physical page frame address. The other one is the present absent bit. And we will see the details of this page table, and we will see that we need more data on this. Other than the address and the present absent bit, we will need some other data. Okay, that's basically it. And it turns out that this structure, implementation-wise, is simpler than base and limit registers, because in base and limit registers we have to add two numbers. Addition is expensive because it needs to deal with this carry bit, right? This one we don't have any addition. We just replace this part of the virtual address number with this part that I looked it up from this table. And looking this up from a table is just a O1 operation, because I know its position, right? It's the 7th position, and etc. So it is easy to implement actually. So basically this is what you do. Okay, you get your virtual virtual address A. It is 16-bit, 48-bit, 36-bit, doesn't matter, whatever it is. You divide it into two, V and O. Okay. O has the number of bits in O is your address for inside your page. Let's say your page is 2 to the 12, okay, bytes. Each of your pages 2 to the 12 bytes. This O will have 12 bits in it, because this O will be used for offsetting. I will transfer this O directly from this location to that location. So V is my virtual page number. Okay, V says that this address in virtual page this. Okay, so that's automatic. That's very nice. I am not doing any arithmetic operations. I am just dividing this 16 numbers into two parts. Okay, one is V, one is O. I know the O. I know the value of O. I know the number of bits in O and V. Okay, V is the virtual page number, and O is the offset within the page. Okay, and the MMU, the responsibility of MMU is mapping this V into P. Okay, how is that possible to do it easily? It is very easy. You just look it up from this array. Okay, you put V into this array, and that array will give you the P. Okay, this one, and you put them together, and that will make your new physical address. Okay, So that will be it. Okay, the scheme is faster than base register. No additions are involved, and that's basically it. Very simple operation, as long as I said, this array is not very large, because if array is large, then my MMU has to be very, very large. I can't keep that kind of large data in my CPU. Remember, MMU is part of the CPU, and I can keep only at most 64 registers, remember, in my CPU, because registers are supposed to be very, very fast, and they are expensive. So as long as this M is not that large, then I can deal with this problem. M will get large, and we will have some ways of dealing with this problem. Good. Any questions so far? So that's basically it. Let's look at these definitions again. So each program has its own address space, and address space is broken into the pages. And the programs, they generate only the virtual addresses, okay? They don't know anything about the physical addresses. They don't know how much physical memory I have on my computer. The programs, they don't care. They say that this is a 64-bit computer. I am going to use all allowable virtual address, okay? They just produce the virtual addresses, okay? And the MMU is responsible for translating those virtual addresses to physical addresses, and it is done by using this page table, okay? So MMU gets, where is it? Okay, gets the virtual addresses, and it outputs the physical address to the memory. My program will always think that it has a nice address space, contiguous address space, and it will continue running without any problems. And again, this will solve all the problems with compaction. Why we don't have the compaction problem? What is the compaction again? Remember, compaction is to eliminate external fragmentation, right? External fragmentation is caused by I am loading my programs in my physical memory, and there are small gaps between the programs, and I can't use them because my programs has to be contiguously my programs need contiguously allocated memory. But in this case, my program doesn't need the contiguously allocated memory in my physical memory. They don't know. They think that they have contiguous memory in the virtual world, and they are fine for that. So no compaction is needed, no relocation is needed, and it is very efficient because it doesn't need any static relocation, dynamic relocation, those kind of issues. Okay. Also, there are some advantages about the protection too. Each page can have its own protection properties. For example, this program. Okay, this program says that I have this virtual address space, and the operating system might say that, okay, these pages are read-only pages. Why would I have a read-only page in my virtual address space? Because these are some code, and you are not supposed to change the code, right? And you are going to share this code with some other process. So it might be something like this. I have another process number 2. This is the virtual address of the process number 2. And this process number 2 has its page table. And some of those might be pointing to these pages. So each one, they are kind of sharing the same page, but they don't know that they are sharing it. Since I made them read-only, they can share this kind of data without knowing that they are sharing the data with other processes. I made them read-only. So this is how the DLLs work actually. Dynamic link libraries. You learned how to do these in your C++ course, I believe. Dynamic link libraries, any library that you have loaded, it will be shared by anybody. So each process thinks that they own the dynamic link library as a read-only page, but in fact they are sharing it with many processes. Okay, so it has these kind of advantages, so we will talk about them too. So by introducing this simple idea, we have solved many problems that we had with my physical addresses. So again, the solution is abstraction. This time the abstraction is the virtual memory and the address space, right? With the memory, and using this abstraction mechanism, we are going to solve lots of problems. Otherwise, would have been a very big problem for us. Good. Let me move on then. Okay, so let's look at in real world, what kind of things we have inside the page tables. This one has to have, we have it. Page frame number, okay? Each entry, remember this one? We have this page frame number and the present absent bit. Yes, okay. We have other stuff inside it too, okay? Page frame number, we already talked about it. Present absent bit, we already talked about it. Let's look at these two bits. These are very important and we will be talking about them a lot. One is a reference bit, okay? Reference bit means that, okay, this program has referenced this page while it is running, okay? So operating system and the hardware is responsible for keeping this reference bit up to date. If that program keeps using this page, its reference bit is always 1. That means what? This page is being used. Don't replace it, because time will come and I have to replace some of the pages with some of the other pages from the disk. When the time comes to replacing pages, maybe I shouldn't be replacing a reference page because it is being used, right? If the page is not used, then its reference page would be 0, reference bit would be 0, then I wouldn't replace it. The same with the modified, okay? So modified means I have modified this page, okay? I have modified this page, so I need to be careful about it. Why do I need to know about this modification bit? I mean, if you modified that page, you modified it already in the main memory, so everybody knows that it is modified. Why do I keep this information? I mean, what is the difference between a modified page and a reference page in terms of handling this virtual address world? Yes?
Maybe we want to save it to the disk later, because we modified it, so we don't have data.
If the page is modified, okay, if the memory is modified, that means that where did I load this page? I have loaded it from the disk, okay? If the page is modified, and if I want to replace this page, you cannot just simply ignore this page, okay? You have to write it back to the disk. If the page is not modified, you don't have to write it back to the disk, you just replace it. So modified pages are more expensive to replace. Why? Because I have to write it to the disk first and load a new one. Unmodified pages are less expensive to replace. That's why I need to keep this modification. Okay, other stuff like the protection again. You say that, is this page writable? Is this page readable? Is this page executable? And etc. You keep that information inside this field of the page table. And caching disabled is this, okay, I don't want to keep this page in my cache. Well, cache is very efficient, I know, but sometimes some pages are sensitive, they are being updated. For example, if I share some part of the memory with the other CPUs, okay, if I share some part of the memory with the other CPUs, it is very difficult to cache that part in my cache, because each CPU has its own cache, if they keep their own copy of that memory location and that memory location is shared, then that's going to cause lots of race issues, right? Race conditions. So I don't want that. So in that case, you are going to mark that as don't load this page in your cache. Always refer to that cache in your memory. Okay? So that's the basic idea of virtual memory and the paging. It was invented, as always, in 1960s, and even today we are using it as the main tool of our memory abstraction. Of course, the things are not as simple as this. Okay, this is not as simple as this. Maybe in these PDP 11 days, PDP 11 was a very simple computer, but for its day, it was like a few $100,000 worth computer. Okay, but it was a simple computer in today's standards. It had only 8 pages of address space. 8 pages of address space. And, well, that means that if you keep 8 registers to represent the table, and that was enough. Okay, that was enough. But nowadays, if you have a 1 gigabyte of memory, and 4K bytes of pages, then inside this memory there are 256 kilo pages. Okay, that's going to be very, very large. You can't keep that kind of data in your MMU. That's too big. We have to do something. We have to do something about it. Okay, so we need a separate page table for each process. That's the other thing too. Okay, this is for a process. Okay. This is for a process only, and obviously each process has its own virtual page table. Whenever I do the context switching, I need to store this page table into my process table, okay, and load the new page table. And this is where the context switching becomes more expensive. Why? Because the page tables are large. Okay, and when you change your page table, it's going to take a while to load it from the memory into the CPU and etc. This is not as simple as saving tens of registers. It is much larger than all of your registers. Okay, so most of the context switch time comes from your memory handling, not from your processes or the threads. It is from the memory abstraction. Okay. So if I have megabytes of data in my CPU, somehow let's say, but it's not possible, but somehow let's say I kept megabytes of page tables in my MMU. Every time I have a context switch, I need to load that megabytes of data from my process table to the MMU, and that's going to make the context switch, which is already slow, a lot slower, and that I don't like it. Okay, so this approach is too simple. We need to do something better, and I am going to spend maybe rest of today to tell you what kind of things we can do to make the page tables faster. Okay, so any questions about virtual memory, page tables, address translation scheme? Everybody's fine? Okay, we will see about that on Monday. And again, this one, let's look at this one. Okay. Yeah, the main memory reference is expensive, we know that. And when you try to load the page table from the main memory, it's going to be expensive. It is okay, 100 times more expensive than accessing your registers. And inside your main memory MMU, you are storing all that information in your register if the table is small. Okay, we know what kind of penalty we are going to have if we don't store my page table in my MMU. Okay, let's look at it. Okay, so where do we keep where do I keep my page tables? Okay, the first thing is, let's put the page table in RAM. Don't put them in my MMU. That kind of solves the problem. Okay, in my RAM, I can hold 1 megabyte of table, right? That's okay. But that's going to be a very big problem, because remember what the MMU does. Let's go to this one. For every memory reference of the CPU, I have to translate that virtual address to the physical address, and that means a table lookup. If I keep that table in my main memory, that means what? I need to go to the main memory, get the page table, and put it back to my address. And that's going to make things 2 times slower, okay? Because I am trying to already access the memory. To access the memory, you need to make another memory access. And I showed you the data, right? Accessing memory is 100 nanoseconds. It is 100 times slower than accessing your registers, okay? So that's not a good solution. That's not a good solution. Okay, keeping your page tables in RAM is not a good solution. That's one thing is slow, and extra RAM access for each memory reference. That's unacceptably slow. And also it takes lots of RAM too. I mean, spending megabytes of memory space to keeping the table is going to be a lot of memory usage, and we like to be careful about our memory usage too. Okay, the modern operating systems, yes, they keep their page tables in RAM partially. Some part of the memory, some part of the page table is kept in RAM. Some part of it, the most used part, is used inside the MMU. That makes it fast, but very large chunk of it are kept on the disk. Okay, now this might come as surprising, because I didn't like the speed of the main memory for the page table. Now I am trying to keep it on my disk, but I have no other solution. Okay, because we are talking about the virtual address spaces of like this. Our modern Intel-based 64-bit computers, their address space is as big as this much. Okay, so I need a page table to hold all the possible pages, and that's going to be larger than my main memory. Okay, physical main memory. So I need to find a solution, and we will talk about that too. So let's speed up the paging. We like to keep everything in MMU. That's too large. I can't do that. Let's keep them in my main memory. That's too large, and that's too slow. I can't do that either. And then if I keep everything on my disk, well, I didn't like 100 times slower main memory. Now I am talking about billions of times slower disk, right? That's even more problematic. So we need to find something like a solution. Remember our memory hierarchy? We had the registers, and we had the L1 cache and L2 cache and the memory, etc. We will find a solution like that. Okay. So speeding up paging, major issues. The mapping from virtual address to physical address space must be fast. Okay. If the virtual address space is large, the page table will be, of course, large. Okay. So 2 things cannot be satisfied at the same time, both being fast and being large. If it is small, we already solved it, PDP-11 way. But it is not. It is large, so I need to keep it large. I need to keep it fast. So I will find a solution just like the cache solution. Remember the cache from your architecture course? We say that cache is a very good solution. Cache is a small amount of memory somewhere in my CPU, and it keeps frequently used data and frequently used instructions in that cache. Okay, and we say that it works. Why? Because of the principle of locality, right? What does the principle of locality say? It says that if you are if you are executing an instruction and if you are accessing some data in your memory, chances are that you are going to execute a nearby instruction and you are going to access a nearby data in your memory. So let's keep that neighborhood of that instruction and the data in my cache, which is much faster. Okay, so by keeping our cache hit ratio high, our programs will run much faster than without any cache because of the principle of locality. Right? The same thing will apply here. This time we are going to use something like the name is going to be translation look aside buffer, TLB. Okay, TLB is kind of a cache that keeps the most frequently used page table addresses in my MMU. Okay, so MMU keeps, let's say, 1,000 or 1 kilo entries of 1 kilo entries of the page table in the MMU. Okay, inside the TLB. And I know that most of my memory references will be through that fast TLB. Okay, as for the caches, TLB is an associative memory. Okay, so you give it a number, you give it a value, and it gives you another value. It is not like indexing. You say that, do you have this virtual address page in you? It says yes. If it is yes, then it will give you the physical page address. If it says no, then that means that's a hit. You have to get that value from your main memory TLB. Okay. So when there is a TLB mess, that means what? I need to get that TLB entry from the main memory, and I need to replace one entry inside my TLB. Okay. And this works because the same principle, our programs tend to exhibit locality of reference. That's one thing. The other thing is that our compilers are optimized to produce code that are good for the cache and the TLBs too. Okay, and if you are writing an assembly, you should be careful about your cache structure. You should be careful about your pipelining structure and your TLB structure too. Okay. So all of these things are done mostly by hardware. Hardware handles the TLB, but for RISC machines, okay, as the philosophy of the RISC implies, it says that I am not going to handle any algorithms as long as they are not critical on hardware. Instead, I am going to give you lots of space, cache space, lots of registers, and you handle everything in software by the operating system. So on RISC machines, this TLB is populated by the operating system. So operating system can make it more efficient and more effective. Okay, so that's why we are looking at this TLB structure, because for RISC machines we are doing it that way. Okay, so TLB is going to be an answer to this problem. If the virtual table is large, then page table will be large. So I like it to be fast. So don't keep the whole page table in MMU. Keep the most frequently used ones, okay, in the MMU. Of course, that doesn't mean that every time I am going to get this translation by the MMU. Sometimes, from time to time, I need to go to the main memory, and that's going to be a mess. We don't like the messes, but that's going to happen. Misses usually happen when you start your program first. Okay, there will be lots of misses, both cache misses and the TLB misses. Also, misses will happen after the context switch time. Okay, another penalty for the context switch. After the context switch, lots of TLB misses will happen. Okay, so here is one example TLB of maybe 1, 2, 3, 4, 8 entries. Okay, inside my TLB, well, it is a little bit different from the my page table entries. In page table entries, okay, I didn't have this column, right? I didn't have the virtual page number. I had the modified reference bed. I had the protection. I had the page frame. But I didn't have this virtual page number column. Can anybody tell me why? Why do I now have to keep this virtual page column inside the TLB, but I didn't have it in my page table? Remember, TLB is kind of a copy of the page table, but only small part of it, most frequently used part of it. So now, why do I have to keep the extra information? Yes?
Because you don't store the whole page table. You're now storing a reference to a page table, and from that page table.
Yeah, exactly. That's because we don't store the whole page table. We store only a small part of it. This one says that I am keeping only the virtual page number 140, 20, 130, and etc. Right? So this is the reason. This is how the cache work, right? I mean, what is the difference between a standard lookup and the cache lookup? For the standard lookup, like this one, you say that give me the entry number 7. Okay, the entry number 7 is here. You just give this address. You just get 000 out. Okay, this is as simple as that. But with the cache structure or the TLB structure, you don't say that give me number 7. You say that do you have the virtual page number 19? This TLB cache structure makes a search. It finds this a line that contains this line 19 here, and it will return you this 50. Okay, 50 is your page frame number. So put 50 at the beginning of your offset, and this is your physical address. Okay, that's how the cache works. That's how the cache works. So that's why we can't keep these TLBs very large. They are fast. They do their lookup in a very special way, but I can't make them large. They are expensive. Good. Any questions? So quietly. Okay. So many risk machines do nearly all of this page management in software. A much simpler MMU. MMU is very simple. It just makes a lookup. Okay. And the rest of the TLB handling, like the misses, replacement of the lines of the TLB and etc., they all will be done by the operating system. So you don't complicate your risk machine by handling this in hardware. That will free up the hardware, and you can use that part of the hardware for extra registers, extra cache, extra TLB area. And overall, it will be a more efficient system. That's the idea of the risk, right? Risk machines are not less complicated than the CSE machines, right? They are as complicated as the complex instruction set computers, but they say that I am not going to be complicated because I am implementing lots of features in hardware. I am complicated because I provide lots of registers and lots of cache and lots of memory for the programs. Okay, so if you are an operating system that work on a risk machine, then you will have to be more complicated in terms of handling stuff. That's what we are going to do. Okay, if there are no questions, I think I will take some break. Where is my attendance? Did everybody sign it? Everybody? Okay. 15 minutes of break. Efendim? Teams'e giremedim ki hiç. İnternet çalışmadı hiç giremedim.
Ben de duruma bağlanamak demek ki.
Tamam, ondan işte. Cep telefonu da harcamak istemiyorum. Mahvettiniz beni ya.
Zaten YouTube'a atıyorsunuz.
Ha?
Zaten YouTube'a atıyorsunuz.
Ha.
Hocam yoklama konusundaki hassasiyetinizi biliyorum ama haftada bir gün anca gelebiliyorum.
Canın sağ olsun, ne diyeyim?
Ha.
Hallederiz diyeceğim ama halletme olmayacak yani. Gel sen bilimsel hazırlıksın değil mi?
Evet.
Yani şey şu, eğer kalıyorsan dersten ne yani veririm ben sana. Geçiyorsan bakıyoruz durum.
Öyle mi?
Ama yaşam durumuna göre.
Evet. Yani o anlamda değil yani. Şey bence o. Hani adam aslında patlarsın. Ama şu an aslında yok galiba.
Okay, so we are going to do the TLB management in software by the operating system, and one responsibility of the memory management part of our operating system will be to deal with the TLB. And to do this, let's see a few definitions. For the TLB, it's like the cache management. For the TLB, a soft miss, okay, is defined as this. It occurs when a page reference is not inside the TLB, but it is in memory. So this is our TLB. When you say, okay, I need the page number 150, you look at this table, okay, I don't see 150 here, so it is not inside my TLB, but that doesn't mean that page is not in our memory. Let's try to write this down, okay? This is our CPU, okay? Inside my CPU, I have my TLB in memory management unit, okay? Inside my CPU, I have my TLB, and this is my memory. In my memory, I have my pages, of course, but I have somewhere my page table. Okay, if I miss, okay, if I do a soft miss, it means that the entry is not in the TLB, but it is in the page table. So page table contains the entry, so it points to somewhere inside my main memory somewhere, but it is not in my TLB. So that means that I don't have to load the page from the desk. The page is already in the memory, but it is not inside TLB. That's a bad thing, but it is not a very, very bad thing. That's why it is called soft mess, and it's going to cost me a few nanoseconds because I need to make a memory lookup. A hard miss occurs when the page itself is not in memory. Okay, that's the terminology. A hard miss is a bad thing, very, very bad thing. It is the worst thing that can happen with a MMU. So it is not inside the TLB. It is not inside your memory. So you have to do a page replacement. Okay. Another term, a minor page fault. Okay. Page faults, you know, if the page that you are looking for is not in the memory, okay, or if the page that you are looking for is not where you want it to be, okay. So there are a few versions of it. A minor page fault is this: page may actually be in the memory but not in this process's page table. Remember, each process has its own page table and they share the main memory, physical main memory, and the physical main memory will include pages for both processes. Let me try to show it to you like that. This is my main memory. It has lots of pages in it. Process number 1, page table, and process number 2, page table. Of course, these page tables are kept inside the main memory, but just to make things a little bit more understandable, I am doing this. So each one is keeping pointers to these areas, and this one is doing the same thing, says here and there, and sometimes they share the same page too, right? So they are sharing the page frames of the main memory to processes. Okay, let's go back to this one, the minor page fault. Minor page fault says that, okay, I need this page, okay, but it looks like it is not in the page table, but that doesn't mean that that page is not in the main memory. Maybe that page is this page. All I am going to do is to make a pointer to that page, and that will be it. So that doesn't mean that I need to make a page replacement. Okay, I don't have to go to the desk to handle this minor page fault. With the major page fault, the page needs to be brought from the desk, okay, and that's going to take milliseconds, and compared to nanoseconds, milliseconds is eternity, right? It's just so long. Okay, we are talking about billions of times slower time stuff. Okay, so that's minor page fault, major page fault. We don't like major page faults. Okay, we don't like hard misses, and we don't like, of course, the segmentation fault. Segmentation fault is this: the program simply accessed an invalid address. What does that mean? For example, an address that doesn't belong to that my process, or an address that I am only allowed to read, not modify, or read, not execute, and etc. Okay, remember the protection stuff: read, write, execute. If I am trying to write to a page table, physical page, that is only read only and execute only. Okay, if I am trying to write to that page, then that's a segmentation fault. Okay, there is no fix for that. That's going to cause an interrupt, and the operating system will handle it. Okay, good. So these are the definitions, and we are going to use them time to time. You might say that, what is the difference between a hard miss and a major page fault? Well, I'm not saying that these are different definitions, okay? Soft miss and hard miss and a major page fault, their definitions are kind of overlaps, okay? Sometimes they explain the same thing. So these are the terms that are used in the operating systems world, and we gave them to you now. Okay. So this is the flow chart of software TLB management. Okay. Whenever I received a new virtual address, this is what I do as the TLB manager. Okay. I check the CPU TLB, okay, MMU TLB. If it is in the TLB, then I just produce the physical address. That's it. I get the page frame number from the TLB entry. Okay, I follow this path. This path is easy to follow, and I already showed this. So this is the simplest case that we have seen before. This is the case where things are like PDP 11, right? I have small number of elements in my TLB, and I am lucky enough to have that element inside my TLB. If page table is not, if the page entry is not in the TLB, then I need to access the page table in the main memory, okay? And inside the main memory is going to be again a little bit slower. If that page in the main memory, if that page is in the main memory, then I update the TLB. That means that I need to replace one of the entries inside the TLB, and I produce my my physical address again. So this path is like soft miss path, right? Okay, it is not in the TLB, but it is in the main memory. If it is not inside the main memory, then we are in trouble. Okay, we need to read that page from the disk, and I will ask the I/O hardware to read that page from the disk, and probably I am going to block this process, causing this page fault. This is a page fault, right? So this process will be blocked, and blocking means that I need to save all of its registers and everything. It is in the block list, and I will ask the hardware to load the data for me. Okay, when the data is loaded, my troubles are not over. The disk driver says that the data is loaded, your page is ready in my buffer, driver buffer, and I need to check if the memory is full. I mean, if the memory is full of pages, there are no free space available in my memory, then I need to replace one of the pages in my memory, right? Okay, because I know that my memory is limited, physical memory is limited, my virtual address space is larger than my physical memory. On top of it, I need to keep many programs in my memory at the same time. Probably my memory is full. What do? I need to replace one of the pages from my memory. That means what? I need to do the page replacement. Okay? So if I do the page replacement, that means I need to take one of the pages out of memory. If it is modified, I need to write it to the disk. If it is not modified, I don't have to write it to the disk, and come back from there, and I update the page table, and go back to CPU checks the TLB thing, so make that process ready again so that it can run. So this is the typical flow chart of what did we say as the software. We are going to handle the TLBs. This is the program that you run in your memory management part of your operating system. Good. Many things can happen wrong. The nicest path that we like is this path. Okay, this green path. I like that. Maybe you didn't see it. Do you see the green path? Okay, I like this green path because everything is the way that I want it to be. If it is inside the TLB, it is fast. I am not going to wait for anything. Okay, if it doesn't happen, then of course I like things to be in the main memory. Then the second most likely path is this one. Second most, the path that I like the second most is this path. Then the third path, the worst one is of course this one. Red one. Okay, it goes like there, and okay, go back to the beginning. It involves blocking the process. Okay, and when you look at it, it's like crazy. I mean, does this really work? Yeah, it works, and it makes things better, much better than not using the TLB or the MMU, okay, or the virtual memory. And our modern computers work this way, okay, paging. You heard about it. And in fact, I don't want to do that, but I'm going to do it anyway. If you go there and with my processes somewhere, these are my processes. Go there. Where do you guys remember where I see my page faults? Where?
Performance.
Performance? Yeah, performance. Then
And in the bottom there is
Yeah.
kaynak izleyicisi.
see the resource monitor. Where did it go? It is this one. Okay.
This is right.
And in that case, so these are the threads that these guys are using it. Okay, CPU times, and let's look at this. Yeah, these are the memory stuff. Can I get it? CPU. I think I can add more stuff to it. I remember Windows gives me the number of page faults a process is causing, but I could not. Maybe, yeah, like this. These are the CPUs. It looks like I have 8 CPUs, and these are the CPUs, all of them. Can I do this? Click on it, and then what? Right click. So I couldn't find it again. Maybe do it this way. This is my memory. So this is modified one, okay? Modified pages. Only 56 megabyte of it. And these are referenced. So these are the reference pages, these are the modified pages. Am I going to see the, okay, I am seeing this for all of them, I guess. And this is empty and this is ready. Okay? So usually the operating systems, doesn't matter how many processes you have in your memory, it keeps some part of the memory in ready state. It says that, okay, these pages will be ready so that my page replacement is very, very fast. I don't have to replace anything, okay? There is always a ready page available in case it is needed. So how do I keep it? It just writes the pages back to the disk whenever they are not used. So it doesn't it doesn't wait until the memory is full, okay? I couldn't find it. Maybe this one? No.
Sorry, is it? No.
It should be inside the CPU, and there must be some kind of an option that says that show me the page faults somewhere. Maybe open these up. Open these up. Yeah, these are just regular CPU stuff. Okay, maybe if I say how to, well, I am not connected to the internet. Anyway, can anybody look it up? Operating systems keep this track of the page faults a process is causing. So if the whole operating system is causing lots of page faults, that means that I am out of memory. That's not a good case. Maybe I should kill some of the processes, because that's called trashing. Okay, let's look at this picture. Typical TLB. Okay, let's say the size of my pages are 4K 2 to the power 12. Okay, my hit time is just 0.5 for 1 clock cycle for the TLP. Miss penalty is 10 to 100 clock cycles. Okay, and my miss rate is around 1%. Okay, if a TLP hit takes 1 clock cycle, a miss takes 30 clock cycles. Okay, so 30 means that, okay, TLP means that I didn't find whatever I am looking for inside the TLP. I am going to go to the real page table inside my memory. So going to the memory will take 30 clock cycles. Okay, and if the miss rate is 1%, the effective memory cycle rate is, okay, 99% of the time, whatever I am looking for inside the TLB, by just looking at the TLB, okay, by just looking at the TLB, I can produce my physical address, and once I get my physical address, I can access the memory by this 30 clock cycles. So accessing the memory takes 30 times more time than accessing the TLB. So I am lucky that 99% of the time, this will be my effective memory access time. I mean, memory, to access the memory, I need to spend 30 clock cycles anyway. So I am going to add one more clock cycle for the TLB lookup. In case I missed my page inside TLB, then I need to go to the memory again. 30 for the page lookup inside the memory, 30 for the real memory lookup, 1 for the TLB, and this will happen only 1% of the time. So the total will be 31.30. So that's the cost of using the virtual memory. Instead of spending 30 clock cycles for each memory access, I am spending 31.30. Okay, and we say that this is worth the efficiency loss, because virtual memory is everything for us. Okay, without the virtual memory, there will be lots of protection problems, there will be lots of compaction problems, inefficiency problems, and not loading the program, many programs at the same time to the memory, and etc. So this is worth doing it. That's what we are saying. Of course, it all depends on this number. Okay, my miss rate is very, very low. Okay, and that should be satisfied by the principle of locality of the reference. Also, it is satisfied by the very, very smart compilers and smart programmers. Okay, your compiler would produce code that, okay, it uses your TLB in an optimal way, and it uses your cache in an optimal way. Okay, that's why many people prefer writing in high-level code in C and use very smart compilers. And there are lots of research about writing intelligent compilers using artificial intelligence technique to write the intelligent compilers. Writing a compiler is as complicated as writing a operating system kernel part of it. Okay, so that's a different route. Good. So we kind of solved the problem, but so what are we saying? We are saying that we cannot keep everything inside TLB. It is too small, fast but too small. So we need to keep the rest of the page table in our memory. But remember at the beginning, page tables are so large, they can't even fit in our memory. Okay, they can't fit even in our memory. So what is our solution? Solution is multi-level page tables. Okay. How to deal with very large virtual address spaces? Okay. The secret is keep a multi-level page table. Okay. Let's look at this picture. I have a 32-bit virtual address on some computer. Okay. It is 32-bit. Virtual address, this 12-bit of it is the offset. So my page size is 12, again 2 to the power 12. It is 4 kilobytes. So the rest of 20 bits is divided into 2. Okay, PT1 and PT2, and this is the case. This is my virtual structure of the virtual address. This is supposed to be 20 bits for the page number, but I divide it into 2. I use this 10 bits to address a top level page table. This is 1 kilo entries, 2 to the power k, 2 to the power 10, top level page table. and obviously this is just 1000, more than 1000 lines of entry. But each of these lines, they don't hold a pointer for the page frames. They hold pointers for other page tables. There are more than 1000 page tables around, okay? Because each one is holding a page table, okay? And I have 1024 entries in this one. So I have 1024 page tables, and each one is holding pointers for pages. Okay? Well, the obvious answer is this. I can't keep 2 to the power 20, okay, 1 mega line of page table in my memory. It won't fit. It is too big. So I keep only this 1K element entry of page table in my memory. And for the rest of them, out of these more than 1000 page tables, I keep the most used of them, okay, frequently used of them. The ones that I don't use, I will keep them on disk. This is called multi-level page table. Okay, multi-level page table. If I am not lucky, my page will not be in the TLB. And if I am not lucky, I always take this 10 bits, look it up. If my page table is in the memory, then I use it. Otherwise, I need to load this page table from the disk and look it up from there, okay? So to access a page, I may need to go to the disk. Once I loaded this from the disk, I look it up, that page. If that page is in the memory, that I am liking. If it is not, then that's the page fault. Okay? So sometimes to access a memory location, you may have to go to disk twice. One for the page table entry, one for the page itself. Okay? And if we carefully design our system, it won't happen much, and we will be happy 99% of the time, which is good enough. Remember our real-time computers? They don't like this kind of stuff at all. I mean, that's why they don't provide protection. Because when they provide protection, virtual memory and etc., and if you have these kind of large page tables, and sometimes it will take you half a second to access a memory location, that's not going to be good for them. So they say that, okay, let's ignore the virtualization, memory virtualization. All the processes, they just use directly their physical memory addresses. So we need lots of memory, and we are going to restrict the processes, saying that you can't do this and this, but no, not to those. Okay. So we kind of sacrifice these kind of nice ideas for the real-time computers, just to keep our promise of meeting the deadlines. Good. So multi-level page table is the answer to the problem of our page tables are not fitting in our memory. Intel processor, okay, 386. It says that I can since it's a 32-bit computer, its address is 2 to the power 32. Okay, so it says that I am going to keep, okay, this is from the Intel actually, I am going to keep my pages as like 4 kilobytes, okay, and level 1 page table, level 2 page table, and that's what I can address. Pentium Pro, 10 years later, in 1995, okay, Pentium Pro says that I will have 1, 2, 3, 4 page table levels, not just 2, 4 page table levels, and again my page table size, my page size will be 4 kilobytes, and I can address in my virtual world 2 to the power 48 bytes. Okay, so it's a very large virtual address space, but using these kind of techniques, TLB plus the multi-level page tables, I can do that. I think our current model, Pentium model, is using this one too, 4-level page tables. Yes.
In that 4-level page table, what is going to be the TLB structure? Because
Did everybody hear the question?
No.
Even you didn't hear? The question is, in 4-level page table structure, how about the TLB structure? Are they going to be different? No, the answer is no. It is exactly the same. This one, okay, we like to be in the green line, okay? Just check the virtual address. If it is inside the TLB, then use it. Otherwise, go to the main memory to see if the page table contains the address. If it is not, then we load it. Well, I mean, when you go to the main memory, now your main memory includes this. I mean, remember this one? 1% of the time you go to the main memory and you get your data from the main memory. This time, if you have 4-level page table, you have to go to the main memory 4 times. Okay? And every time there is a risk of not seeing that page table in the main memory. So every time there is a risk of loading that data from the disk. Okay, so in that case, there might be like 4-5 different accesses to the disk to load the relevant data to access a single memory location, just for the virtualization. Again, 4-5 different accesses, sequential access of disk, is going to take you like a second, and that's sometimes why you wait. Some programs just simply wait. I mean, especially when you open them up, okay, the first time you launch them, you wait for no reason, just wait and wait, and it's because all the page tables are being updated, the cache is populated and that kind of stuff. Sometimes this happens with the context switch if you have too many programs in your memory. Okay, good. So some people said that why do we have to keep the page tables that way? What was the idea of page table? Page table is, okay, if my memory is 2 to the 48, this is the virtual address space, okay, let's take out the 12 bits for the page size, 2 to the 36, okay, so I need this many entries in my page table, whether it's a multi-level page table or a single-level page table, whatever. Okay, so I need this one will keep. Okay, compared to this 2 to the 36, my physical memory is very, very little. Okay, so I need to do this. Okay, pointers and pointers and pointers, and most of this page table will be empty. Most of this page table will say that I don't have this in memory. I don't have this in memory. So they are all invalid. Okay. Some people say that, well, this is too inefficient. Why are we keeping them like this? This is like a sparse array, right? To keep these kind of sparse arrays, do you have any idea from data structures course? I am going to make a lookup. I am going to say that, I mean, what is this value? Give me the index number 7, and it will give you the index number 7. And most of the time it's going to tell you that I don't have it. Okay? And I like to do it fast, but I don't want to waste lots of space like that. So how do you do that? From data structures course again?
Hash table.
Hash table, yeah, exactly. Hash table. Just why don't we use a hash table? Okay, when I get the virtual address here, okay, hash it up, and it will give you, and use a small table like that. Okay, get this one, and this hash table will tell you that, okay, I have it. And one type of hash table is, remember that the ones that uses the linked lists, okay, say that, okay, your place is here, and I'm going to give you a linked list of pages, okay, page table entries, and you can use them. That's the idea of inverted page tables, okay. We don't like to keep, okay, we don't like to keep one entry per page of the virtual address space. We don't want this, okay. We don't want to do one entry per page of virtual address. Instead, we like to keep one entry per page frame in real memory, okay. So our table will be as small as the number of pages in our physical memory, not like the number of virtual pages. Up to this point, all the page tables that I have drawn, they include that it includes the number of one entry per virtual page, but in my physical memory, there are a much smaller number of page frames. So this inverted page table says that, okay, I am going to keep one entry per page frame in real memory, okay, and so I save lots of space. I don't have to think about this using more than one level stuff, etc. But it requires me some hashing, okay. My access will be O1, an average time O1, right? It's like the page table access. It's going to be O1, but it will require me doing some hashing. That might take some time, but if our hit rate is not that bad, that time will be justified because my page table will be very, very small. I can fit the whole page table in my main memory. Then I don't have to deal with the disks and that kind of stuff. Okay. When process and references virtual page P, okay, the hardware can no longer find the physical page by using the P as an index. So array lookup is not possible anymore. Instead, we must make a search, and that search is going to be done by hashing. Okay, so that's the inverted page table idea. This is the classical page table. Okay, for a 64-bit computer, if my again page size is 12 bits, you need to have this many entries, 2 to the 52 entries in your page table. That's the classically what you do. Okay, instead I am going to do this. If I have a 1 gigabyte of physical memory, okay, 1 gigabyte means that 2 to the 30, right? So take 12 out, 2 to the 18 elements. So if you compare this one with this one, the difference is huge. Okay, difference is huge. And I am going to keep this like a hash table. Whenever a new virtual address comes in, I look it up, of course, the virtual page number. I look it up inside my hash table. If there is a hit, okay, I get a linked list. I traverse the linked list. I get my page out of it. Okay, page frame out of it. If it is a miss, then it's a miss. It's the same thing as before. Okay, by spending maybe a little bit more time, I am saving huge amounts of memory. Saving huge amounts of memory means that I don't have to go to the disk anymore, or I don't have to go to the disk as frequent as before. Okay, so that's the idea of the inverted page tables. Another solution to the problem of large page tables. Okay, good. Again, let's go back to the context switch time. Most of the context switch time penalty comes from the page faults, okay, or the paging. When you switch from one process to another process, you have to update the MMU tables. You have to update the MMU TLB tables, and you have to sometimes load new page tables from the desk. Okay, that's what makes most of the time your context switch time slower. It is because of the memory management. Okay, so we kept talking about replacing the pages, but we did not talk about how we do that. As the operating system, we are responsible from it. Let's look at these algorithms. Now we are talking about, this is my virtual memory. This is my physical memory, right? Virtual memory and physical memory. If the page this virtual memory is referring to is not in my physical memory, then I have to load the page from the disk. This is my disk or secondary storage. But when I load it, usually there is no room inside my physical memory. I need to replace one of the pages. If there is enough room, then no problem. But usually there is not enough room, okay? So I need to select one of them to say that, okay, I don't need you. Well, I need you, but I don't, there is somebody else whose memory request is more urgent. I'm going to replace you. I'm going to put you back to the disk and I'm going to load it. So how do I select that page? That's called the page replacement algorithm. There are many algorithms, and some of them, for example, this one is not implementable. It is optimal, it works perfect, but it is not implementable because this one says that I would run a simulation of the program. After running the simulation, I can make a decision. So it is like running the whole program and later coming back and these are the decisions, etc. So this doesn't work in real life. It is only good for knowing that how good you are, okay, how close you are to the optimal algorithm. Well, I already told you the algorithm, it is not implementable. So we are going to use it for reference. Not recently used algorithm, first in, first out algorithm. These are just for algorithms for me to tell you how the things work. Starting from these algorithms, okay, these are some real page replacement algorithms. Okay, so let's look at them one by one. Whatever algorithm you are running, okay, these are the constraints. You need to obey these rules. You have to be efficient. This is a very critical part of the operating system page replacement. To be more effective, to be more, let's say, to make better decisions, if you are going to take a day to make a calculation, that's not going to be good. You need to be efficient, okay? So you spend less time, you give a good decision, you produce a good decision. You have to be efficient, okay? And it must approximate the correct answer. What is the correct answer? It is the optimal page replacement thing. So we are not saying that you have to be optimal. We cannot be optimal, but you have to be close to the correct answer. And the algorithm must be implementable on real hardware, okay? If you say that I need the hardware hub to implement this and this and this, but no such hub is available, it is too expensive, then it's no use. And usually it must work well on multitasking systems. That means that don't assume that you have a single process only. You will have more than one process most of the time. So these are the constraints. We will keep these in mind. And while we are making a decision which page to replace, these are the tools that are available for us, okay? For example, for each page table entry, I have the reference bit and the modified bit, okay? I think most of the time, if a page table entry has a reference bit 1 and modified bit 1, okay, I don't want to replace that page because somebody is using it, right? If both of them are 0, then why not replace it because nobody is using it? So we are going to use these 2 bits a lot, reference and modified bits. We are going to rely lots of clock interrupts. Remember the interrupts, timer interrupts? It happens like 40 times a second. Every time this clock interrupt happens, for example, I am going to scan the whole page table. Well, that's a very big thing, right? I am going to scan the whole page table and mark all the page table entries that did not get referenced, or maybe increment their reference number and etc. Okay, so I am going to run an efficient algorithm every time the clock interrupt happens. Remember when I told you that clock interrupts are not used for process scheduling or the thread scheduling or the preemption. Okay, we use clock interrupts for many things, many housekeeping things by the operating system, and one of them is this: keeping the process page table updated. Okay, the other one is page fault interrupts. Page faults happen when the page that I am looking at is not in the memory. It is automatically produced by the hardware, by the CPU. Okay, and if the page faults happen a lot, then as an operating system I need to do something about it, and that's another tool for me, so I am going to use that information. And finally, sometimes the application gives me the clues. The application says that, well, although I'm not supposed to know about the pages or paging, well, I know a few things or two. I will tell the operating system that this part of the data is important. Keep this in memory. Don't write it to the disk. Okay? So that's the advice from the application. Although I did not use this page for a long time, I am going to come back to it. So don't write it back to the disk. I will use it. So that's the advice from the application. Well, I mean, maybe we should take this advice in a careful way as an operating system, because sometimes people have bad intentions, sometimes they do it unintentionally. So we need to be careful about this one. For the others, for the rest of it, there are tools. Nobody can, for example, nobody can fake us saying that this page is modified even though it is not modified, because page table is in the kernel space. To modify the page table, you need privileged instructions. To do anything about the memory management unit, you need the privileged instructions. Okay, so I can trust any of them, no problems, but this one I need to be careful because it comes from the application. Okay, so let's look at this optimal algorithm. It is simple but impossible to implement. Optimal page replacement algorithm, it says that, okay, the page that will not be referenced longest should be replaced. This is nice, right? If I knew the future, if I knew that this page will not be referenced longest, then I should replace it. I don't need it. But I don't know the future. Optimal algorithm says that I know the future because I am running this program now. I can see the future then. I can come back and I can tell you that you should have kept this page in memory or you should have replaced it. Okay? So it is not practical. It is just to compare your results with the optimal results later, after everything is run. Okay? So it needs simulators. It's not a real thing. So optimal algorithm is like that. The first one that we are going to look at is the simplest one, not recently used algorithm. Okay? At page fault means what? I need to replace one of the pages. Okay? I am checking this. For each page entry in my page table, okay, I look at the R and M bits, okay, and I group my pages into 4 classes. Class 0 is this. If a page is not referenced or not modified, it is class 0. Class 1 is a page not referenced and modified. Class 2 is referenced but not modified. Class 3 is referenced and modified. All of them. Okay? So I have 4 different classes of pages. This not recently used algorithm says that replace a page from the lowest class number. So first replace the pages with class 0. It is kind of obvious, right? If a page is not referenced or modified, then I would replace it. I don't need it. So remember what we are trying to do? We are trying to find a page that will not be referenced longest. Okay? Since we can't see the future, maybe by looking at the history, I can make this decision. If a page is not referenced and not modified, maybe that page will not be referenced for a long time. So I am going to replace it. If no such page is available, then I would replace class 1. Not referenced but modified. Well, the reason why we are choosing class 1 over class 2 will be clear in a few minutes, but maybe I should tell you I didn't tell you the whole story about it. Maybe I should ask you this one. How could this happen? How can I have a page in my memory that is not referenced or modified? Who loaded it? If a page is loaded in my memory, somebody has referenced it, right? Why would it be loaded otherwise? Yes?
First time that the process is...
Well, usually the first time when the process is loaded, you don't load all the pages, right? If you try to load all the pages, that will be too many pages, right? You start running the program. The program says that I need this page and this page, and at the beginning of a program, there will also page faults. So you don't load any pages that are not going to be used. Okay. So, yeah.
But you make an assumption that some might be used. For example, if they are the neighboring ones, you might load them. You might use them.
No. Yes?
BIOS, maybe.
What?
BIOS.
BIOS? Well, you are talking about very, very rare cases. Maybe BIOS loaded it. No, it is not. Yes?
After closing the program? After closing the program?
After what?
Closing the program? Exiting?
What does it say?
Terminating.
Terminating the program? No. Well, I mean, if the program is terminated, all the pages are gone. They are all invalidated.
Maybe there is a timer that counts the total time of the available or activation period.
Well, I think what you are guessing is right. I didn't tell you the whole story. The algorithm is not just this. The algorithm is this, okay? On each clock interrupt, scan your page tables, okay, and clear all the R bits. Okay, remember the clock interrupt? It happens 40 times a second. Every time clock interrupt happens, okay, remember your page table like this. One of them is an R bit and the other one is an M bit. Make all the R bits 0. So every 50 milliseconds, all of your page table R bits becomes 0. So I assume that we start from the beginning. So this R bit basically means in this case, nobody has accessed this page in the last 50 milliseconds or 40 milliseconds. So since the last clock interrupt, nobody has accessed it. Okay, that's the algorithm. After that, okay, at process start time, reset all R and M bits. Okay, but when you access those pages, they will be all R's will be 1. When you modify them, M's will be 1. On each clock interrupt, clear all the R bits, and every time you need a new page replacement, you check these classes. So R0, M0 means that, okay, R0, M0 means that nobody has modified this page at all, and nobody has accessed this page since the last clock interrupt. Okay, since the last clock interrupt. So that's the idea of the not recently used algorithm. Not a very good algorithm. Nobody uses this, but it's a good way to kind of start what kind of things we can use. Remember the tools in our arsenal that we can use to address these problems are in embeds. That shows how we can use this stuff. It looks like I am way out of my time. I will stop at this point. So the midterm will include this not recently used algorithm on Monday. Our midterm is on Monday, right? Monday morning I will not hold a lecture, so you study for the exam. And everything in the book, including this not recently used algorithm, line by line, including the footnotes and the exercises and the index section and the contents, everything you are responsible from it, and that includes your homework too. Okay, your homework and your TA's problem sessions. Okay, that will be it. Thank you.